Right. Got that?
Yeah.
Okay. So, I think, Bello, this is the slides where I put Brownian motion into it, I think. Now, if we look at the word thermodynamics, we could figure out what it means. So the prefix thermo, what is thermo to do with? Heat, yeah. Dynamics? Movement. So thermodynamics? Yeah, the study of the movement of heat. You know, thermodynamics studies the movement of heat. Well done on using your English. Between different objects. Now that's enough for you, so you can write that much down. Got that? Yeah. Now, you don't have to write this part down, but it's worth hearing that thermodynamics also studies the change in pressure and volume of objects. I mean, that's kind of obvious. And statistics is also used in thermodynamics. And thermodynamics is useful because it helps us understand the world of very small atoms, how that connects to the large-scale world. We saw an example of this already. Do you remember when we did the formula E energy equals 3 over 2 PV? Yeah. This links the large world of pressure and volume to the small world of kinetic energy of particles. Okay. So look, we've seen that the kinetic energy, yeah, the kinetic energy equals 3 over 2 PV. But also note that we have the formula PV equals NKT. Now let me just write these two down. We know that energy equals 3 over 2 PV for the gas. Okay? Now this one we said has no potential energy, right? So this is really just kinetic energy. But we also know that PV equals NKT. That's when I'm using the Boltzmann's constant number of molecules or atoms or whatever it is. Yeah. If I combine these two formulas, I get E equals 3 over 2 NKT. Or in other words, I could divide by N. E over N equals 3 over 2 KT. Now, what do you think is the meaning of E over N? Yeah, but what does this represent? Energy per molecule, per particle. So it's kind of like an average energy, isn't it? The sort of average energy per, we'll call it molecule, yeah? Average per molecule, and that's equal to 3 over 2 kT. Now, the 3 over 2k is actually just a constant, isn't it?
Yeah.
So you could arrive at this formula, or this relationship. The average energy per molecule is proportional to the temperature. Now that's very significant. What that says is, if I double the temperature, what happens to the energy per particle? Doubles. If I halve the energy, if I halve the temperature, then I would half the energy. And what would happen if the temperature was 0 kelvins? No energy per particle. So what would that mean for its motion? 0 motion. Stationary. So when something is at absolute 0 Kelvin, what are the molecules doing? Nothing. They've stopped. Yeah, completely stationary. Solid as can be. Yeah? Say again? You tell me. It's 0 Kelvin is absolute 0. Minus 273 Celsius. Yeah? Now, that little proof I would like you to write down, and this result is rather important. Did you write this down? Yeah. So, we have a minimum temperature. We said the minimum temperature is 0 Kelvin, right? What do you think? Could there be a maximum temperature? Could there be a maximum temperature? Oh, there's a minimum temperature, 0 Kelvin. Can we be below 0 Kelvin? No, because once the particles stop moving, that's the end of the story. Could there be a maximum temperature? Depends on the molecule, yeah. So, for some particular, for whatever molecule you want, could there be a maximum temperature? You think no? You think yes? Yeah, there is such a thing as a maximum temperature. Okay? And the reason for this is because as the molecule vibrates, the faster it vibrates, it has more kinetic energy. More kinetic energy means more temperature. Is there a limit to how fast the molecule could vibrate? Yes, there is. Yeah. Nothing can vibrate faster than the speed of light. So there actually is a maximum temperature because there is a maximum vibration. Okay? So I think that's interesting. Temperature does have a minimum and a maximum.
Equal to speed of light.
What's that?
Like, can something be equal to the speed of light?
No, it would always be slightly less than it. So there is a sort of theoretical limit to temperature. And you could never really reach it. It's like an upper limit. Okay. Now, I don't think this... Yeah, we kind of mentioned all of this. So, yeah, we have all this. I've mentioned all that. Okay. Next thing to talk about is internal energy U. Anyone want to guess at what the meaning is of this? Internal energy? Go on. It's energy that's internal? Yeah, go on. And what the heck does that mean?
Energy within a molecule?
Not within a molecule, but within a gas, perhaps. So, internal energy of a material is the sum of the kinetic and potential energy of each molecule in the material. So, as a formula, you could write it as U equals total energies, which equals total kinetics plus total potentials. getting all the messages. If you could silence your phone, please. Was that you?
Yeah.
Who's sending you all these messages?
My sister.
Oh, what does she want? Does she not know you're in physics class?
Also, it's your girlfriend.
No. I trust him. He looks honest. Aye, he's honest. He looks honest. Okay, you got this? No?
We need to see all of this one.
If you gave the first sentence and the formula, you probably are all right. Continue?
Yeah.
Okay. So, now we get to talk a little bit about Brownian motion. This is the question you had in the homework, yeah. Describe an experiment that demonstrates Brownian motion and discuss the evidence for movements of molecules provided by such an experiment. So, would I do the experiment first and then the motion? Yeah, okay, I will. We all know that a gas is made up of particles, of molecules, okay? But people didn't always know that. So there was an experiment which was done to see that the gas is made up of molecules. And this is the experiment. I think it was something like you had a box here. And this here was a smoke source. So it could have just been, something like a candle. And you have the smoke filling up this box here like that. Okay? And then what you also have here is just some way to look inside the box. A viewer. You can look inside. There's the eyeball looking inside. And then I think sometimes you can... No, I think the smoke is enough, but sometimes people use pollen, but I think the smoke's enough. And you'll also need a little bit of light as well, so we'll put our light source here. Something like this. So it's a very simple experiment. All you're really doing is looking through. It's not quite a microscope. It could be a microscope. Maybe it's more like a magnifying glass. Maybe it lets you see things 10 times bigger. Something like this. Okay. What you're doing is you're looking at the smoke particles. You could use smoke, or you could use something like pollen. You know pollen? Yeah. It's the little particles that are on flowers. It's what makes you sneeze. Yeah. Anyways, when you look at it, this is what you see. Maybe you look at a smoke particle and you see it moving around like this. It kind of moves around sort of randomly. Okay. Now, what's the reason for this movement randomly? Like when you look at the smoke particle, it kind of dances around. It just moves randomly like this. What's the reason for this? Well, what's happening is this. The smoke particle is rather big. You can see it with the magnifying glass. What you can't see are the air particles. Like, for example, what's in air? Nitrogen, isn't it?
Yeah.
That's N2, isn't it? Yeah. What you can't see is the N2. The N2 would strike into this smoke particle, and what would happen to this particle? Which way would it move? It would move this way. Yeah? And then this one would strike into it, and then it would move this way. So it's getting hit randomly by the nitrogen, and this causes it to move in different directions. So you can conclude the large smoke particle is being struck by unseen, random N2 particles. Therefore, air is a collection of particles. And of course you can put different gases inside. You could put helium or hydrogen or whatever, and you get the same result. So in other words, therefore, gas is a collection of particles. Collection of particles. I know, but because it's 70%, you know, it's mostly N2. Air particles. Air particles are N2, O2, CO2, and others, yeah. It's mostly N2. Yeah. Now, in the exam, you've noticed that they sometimes ask you for the Brownian experiment. This is the Brownian experiment, and the conclusion they also want. So, you really need all of this to answer the question, I'm afraid. Jeffrey, or Kay Hong, do you mind closing that blind? I think it would help a little bit.
Yeah.
Yeah, that's a bit better. And maybe you could close that one. I think there's a lot of light coming through those two. No, that one's not too bad. It's those two I feel a lot of light coming through. Yeah. Okay, continue. But air isn't there is no air particle. Do you know what I mean? If you prefer, Bella, what you could say is you could fill the box with nitrogen or whatever. Continue. Continue? Yeah. I need to push on. Sorry, if you missed it, you'll have to grab it from the video, okay? Right. So, Brownian motion is the random motion of particles in a fluid, or liquid or gas, what a liquid or gas, resulting from their collision with fast-moving molecules in the fluid. Okay, so you'll need, this is the definition of Brownian motion, if you can write that down.
Sorry, I was told like movement of the fly can also be considered as Brownian motion.
No, it's particles. Well, no, not. It's like Brownian motion, but I wouldn't say it is Brownian motion. That sounded like Candy Crush or something. No, what is it?
Stock.
Okay. You got this? Got this?
Yeah.
Okay, I'm going to skip this. We don't need this for the exam, and there's still lots to do. What we do need is this one though. Heat supplied Q. That is the energy pumped into a system. So I'll give you an example. If I put my coffee cup onto something hot, then the energy that travels from this to the coffee cup, I call that Q. Okay? It's called the heat supplied. So like for example, you know, if I was making some eggs, the heat that goes into the eggs is the Q. Yeah?
Yeah.
Okay. Can I continue? So, I already gave an example. Now, does anybody know thermal equilibrium?
What is terminal?
That's what I'm asking. Does anyone know thermal equilibrium? Yeah. Yeah, the sort of input and output is the same. Two physical systems are in thermal equilibrium if no heat flows between them. So, my hand and the coffee cup. If the coffee cup feels hot, then where is the heat moving? It is moving from the coffee cup to my hand. They are not in thermal equilibrium. If the coffee cup does not feel hot, then it means the coffee cup and my hand are the same temperature. There's no heat movement. So they are in thermal equilibrium. This room and the heater. If the heater is on, are we in thermal equilibrium? No, because heat flows from the heater to the room. If the heater is off, there's no heat flow. So, thermal equilibrium. If you shake someone's hand and their hand is cold, thermal equilibrium? No, because heat is going from your hand to theirs. You understand? Yeah. Basically, if they're the same temperature, it's thermal equilibrium. Yeah, continue. Oh, I have this slide twice for some reason. Okay. Here's a simple train engine. What is Q here? Q is the heat energy from the coal that goes into the engine. Okay? What's the delta U? That's the change in the internal energy. What happens to the water? Well, it obviously gets hot. And W is the work done. What's the work being done here? Yeah, the kinetic energy. Yeah. Now, do you notice you actually have conservation of energy here? What's the energy that goes into the system? Heat, good, which is which letter? Q. And then what do we see afterwards? We see work done and the engine gets hotter. So if you were to put these three together into a formula, what would it be? Q equals delta U plus W. That's often written in this form. Delta U, I think, well actually, no. Just for right now, you could write it like this, please. Okay, you got that? Right, next now. Yeah. In the last diagram, heat energy was put into the energy, and the result was, I think I should have said into the engine, and the result was an increase in internal energy and work done. However, it is possible to do work and see an increase in the heat energy. Now, I want to give you a very simple experiment here that was done by James Joule here. So you don't have to write this down, but in his experiment, what he did was he hung this here and measured the height. What type of energy does this have? The potential energy. Okay. Then what he did, he's connected it up into this, and you see these two guys here? They rotate. They spin around when this falls. So this falls slowly, and this spins around. And this guy here, this is a thermometer for measuring temperature. Yeah, heat can be calculated. So what he noticed was this potential energy here gets converted into, yeah, which would mean temperature here increases. So what Joule's proved was you can change work into heat. It's kind of the opposite of what happens here in this slide. The heat here gets used to produce work, make the train move. This picture here, it's the opposite. The work gets used to make heat. You can actually go both directions. Do you understand? Yeah. So you can kind of think about it like this. You can say work is Q minus delta U, or delta U is Q minus W. You can think about it both ways. You can use a change in the, you can use energy supplied to make work, or you can do some work to make a change in the temperature of the water. You know, because you don't need to write this down. I just want you to show that you can move in both directions here.
Is this like representing somewhere equilibrium?
No, it's just really conservation of energy again. Right, so the last thing to do is we have 3 laws of thermodynamics for this lesson. Okay? The first law is called the zero law. And the zero law states if 2 objects are in thermal equilibrium with a third, then they're in equilibrium with each other. Right, before you write this down, let me explain.
Is this 0 or 0?
Zeroed, yeah. I hold this phone. I don't feel any heat. Is my hand and phone in thermal equilibrium? Yes. I hold this coffee cup. I don't feel any heat. Am I in thermal equilibrium? Yes. Therefore, I know that those two are in thermal equilibrium as well. That if I put my coffee cup on my phone will not feel any heat, and my coffee cup will not feel any heat. You understand? This is obvious, right? If my hand and phone are at the same temperature, and my coffee cup and hand are at the same temperature, therefore, those two are at the same temperature. Right? Okay, so write that down.
This must be remembered.
Yes.
Or of the vocabulary must be correctly.
Roughly correct.
This must very busy.
Very busy, I know.
Yeah, before the exam.
Okay?
Second.
Okay. No, I can't. Next one. The first law of thermodynamics is conservation of energy. Basically, what you wrote earlier. Delta U equals Q minus W. That's the first law of thermodynamics. Okay. And lastly, the second law of thermodynamics states that heat cannot spontaneously flow from cold to hot. This is quite simple and obvious, actually. When you put something hot beside something cold, which way does the heat flow? From the hot to the cold, or the cold to the hot? Yeah. Yeah. You put some ice beside a fire, the ice gets hotter, not the fire, right? Yeah, it is possible to actually move the heat from the cold region to the hot region, but you would need some kind of system to do this. For example, you're in your car and it's quite hot outside, right? So what way will the heat move? It'll move from the outside of the car to the inside of the car, right? And therefore you will feel hotter. Seems obvious. But you could turn your AC on, and what would happen? You'll start to feel colder. So what's happening is the AC system is doing work. It is pushing the heat that's trying to come into the car out of the car. In other words, it's forcing it back where it came from. So you can have heat go the opposite direction, but you need some kind of system to do this, some system of work. You know? I like a fridge as well. The freezer will take the heat that's it'll push the heat back out in the opposite direction to how it would naturally flow. So in other words, Bello, you have to do work to make the heat go the opposite way. And that is possible. But it naturally will go from hot to cold. Yeah? Is that okay? Yeah. So you put your ice cream in the fridge, that's cold, the room is hot, the heat wants to go from the hot room to the cold ice cream. To force it back the other way, you need a special pump system that the fridge has. Okay. So, look, I just want you to spend maximum 5 minutes trying a couple of these. No, we'll go to the next topic.
We didn't do maths today.
We just said we'll do it tomorrow, didn't we? Yeah. Right.